I chose this area of research from the really simple perspective that I just thought these materials were cool. I love the applications. I love the idea that the work we do in my group might benefit society in some really fantastic way. But from a really selfish perspective, I just think these materials are cool. I love thinking about how energy moves around at the nanoscale, what form energy takes in its most microscopic embodiments, the way they move around, interact with each other, interact with other molecules in the environment. These are the types of problems that really get me excited, and that's where my research group has established its focus. Almost all of the semiconductor nanomaterials that we work with in my group are so-called colloidal semiconductor nanomaterials. And that means that these nanomaterials are suspended in a liquid suspension in some sort of solvent. And so you can imagine them as a bunch of tiny nanoparticles floating around in a solution. And the advantage of them being dispersed in a solution is that when it comes to manufacturing a device or building your solar cell or building your LED, you can fabricate these devices using solution process strategies. So you can imagine fabricating a solar cell by spray painting this type of solution processable electronic material on your roof. You could imagine printing an electronic circuit on some flexible piece of plastic the same way you print a newspaper. You could imagine inkjet printing electronic circuits and active components. So that's one of the powerful aspects of solution processability of these materials. So one of the primary tools that we use in my group are femtosecond duration laser pulses. These are events that happen faster than can be measured by any computerized electronic clock. And so the only way we have to measure these extremely fast processes that are happening in materials is through using these really short duration pulses of light. One of the really lucky things about being a professor at MIT specifically is the ability to attract some of the brightest minds in the world. And these students and postdocs are just incredibly creative, incredibly hardworking, and really are the drivers behind everything that happens in the lab. I see my role as a facilitator. My role is to provide them the resources they need, the critical feedback they need to be successful, but really all the scientific discoveries are accomplished by the students and postdocs in the lab. I was extremely honored when I was notified that I had won the Camille Dreyfus Teacher Scholar Award. I was particularly excited about receiving this award because I thought it recognized both aspects of my career here at MIT, which I value a lot. And so on the one hand, that's research in the chemical sciences that's trying to push new frontiers in our understanding of nanostructured materials. And on the other hand, that's a commitment to undergraduate education and trying to make sure that we balance our research with our devotion to the students in the classroom. I think a big part of getting students excited is showing them how excited you are about what you're doing. And it's hard to convince someone else to be excited about learning something if you yourself, as the teacher, think it's dull. Students at MIT are a curious mix. They have many different dreams and aspirations. Some of them are aspiring to be traditional chemical engineers, work in the chemical process industry. For a big fraction of them, their dream is to do something that no one's ever done before, and they can't even imagine what that might be. And so our job here at MIT is to fill them with the basics, fill them with the knowledge that'll prepare them to do whatever it is they might choose to do.